probably woke up this morning assuming something very simple, that the universe exists, that matter exists, that you exist, but according to the deepest laws of physics, none of this should be here. Not the Earth, not the stars, not your hands holding a phone. In fact, if the early universe had followed the most basic, most symmetric, most fair rules of physics, everything would have vanished in a flash of light, bold, maybe even arrogant. But let's talk about why the universe should not exist, and why the fact that it does might be the most extraordinary accident in all of reality. Let's rewind 13.8 billion years. The universe is hot, incredibly hot. So hot that matter as we know it doesn't exist. No atoms, no stars, just a dense soup of pure energy. And from that energy, thanks to Einstein's famous equation, E equals mx squared rec, particles are constantly being created. But here's the rule. Whenever nature creates a particle, it also creates its mirror twin, matter and antimatter, an electron and a positron, a proton and an antiproton, proton and an antiproton, perfect opposites. And when matter meets antimatter, they annihilate, not explode like a bomb. They simply disappear, converted back into pure light, completely, cleanly, instantly. So let me ask you something. If the early universe created matter and antimatter in equal amounts, what should have happened? They should have paired up. They should have annihilated. They should have left behind nothing but radiation, no atoms, no galaxies, no chemistry, no biology, just light, a sterile ocean of photons. The laws of physics say symmetry is beautiful. And symmetry says equal amounts. So why are we here? Here's the astonishing part. Here's the astonishing part. For every billion pairs of matter and antimatter particles, there is roughly one extra particle of matter, $1 out of a billion. That tiny imbalance, 1 part in a billion, is why everything exists. After the annihilation frenzy ended, all the pairs destroyed each other, and that tiny leftover fraction, that became the stars. The planets, you are the cosmic remainder. The universe is what's left over after an almost perfect cancellation. Now think about that. Imagine shuffling a deck of cards. If I tell you the deck should be perfectly split, 26 red, 26 black, that's normal. But imagine you shuffle a billion decks, and somehow every time there's one extra red card left over. Not because you cheated, not because someone intervened, just because the fundamental rules slightly prefer red. That tiny bias would completely change the outcome, and that's what happened to reality. But why? To answer that, we have to go microscopic. At the level of fundamental physics, particles follow mathematical rules, symmetries. One of the most powerful ideas in physics is that nature doesn't care about direction, or charge, or time flowing forward versus backward. These symmetries are encoded in the equations that describe the universe, and most of them treat matter and antimatter almost perfectly equally. Almost. In the 1960s, physicists discovered something subtle. Certain subatomic processes involving particles called kaons and later B mesons violate a symmetry called CP symmetry. That's charge C and parity P. In plain English, the mirror version of reality behaves slightly differently from ours. It's like discovering that your reflection in the mirror doesn't move exactly the same way you do, just a tiny delay, a tiny asymmetry, and that tiny asymmetry is enough. The laws of physics at a deep level are not perfectly fair. Matter is slightly favored. And because of that microscopic favoritism, the macroscopic favoritism, the macroscopic universe exists. This is the micro versus macro story. At the microscopic level, tiny quantum interactions, subtle symmetry violations, 1 part in a billion spheres, 1 part in a billion at the macroscopic level, galaxies swirling for billions of years, black holes, DNA, consciousness asking questions about itself. It's like the difference between air molecules in a room and a hurricane. At the molecular level, particles just bounce randomly. At the molecular level, particles just bounce randomly. At the large scale, you get organized rotation, a storm powerful enough to reshape landscapes. Small biases, when amplified by time, become cosmic architecture. Now here's something even more unsettling. Imbalance we measure, the amount of CP violation we know about, is not enough to explain the matter dominance we see. Not even close. Which means something else happened in the early universe. Some process we don't fully understand called baryogenesis. Tipped the scale, maybe new particles. Maybe physics beyond the standard model. Maybe something we haven't even imagined yet. The universe is whispering. There's more to the story, and that's deeply exciting. But let's step back. Why does annihilation happen at all? Dire, because when matter and antimatter meet, their properties cancel. Positive and negative charges, opposite quantum numbers. It's like adding +1 and -1. The universe loves balance. In fact, if you zoom out even further, the total energy of the universe might actually be zero positive energy from matter, negative energy from gravity, balanced. So in some strange way, the universe might have come from nothing, without violating any conservation laws. And yet, even within that grand balance, this tiny asymmetry appears. Why not perfect cancellation? Why not absolute symmetry sad? Because absolute symmetry sad. Because absolute symmetry means absolute nothingness, and nothingness cannot ask questions. Here's an analogy. Imagine filling a perfectly sealed box with gas. But over time, they spread evenly. Why? Because there are vastly more ways to be evenly. Why? Because there are vastly more ways to be evenly spread than clumped. Probability favors uniformity. In the early universe, annihilation was like gas spreading out. But probability is not destiny. If there's even the slightest bias, even the tiniest tilt over billions of interactions, that bias wins. It's like a casino with a 0.1% edge. The house always wins. In this case, the house was matter, and we are the winnings. Now let's address a tempting counter-argument. You might say, okay, but if the universe slightly prefers matter, then that's just how it is. No big deal. But think carefully. If the laws had been even a little different, if the asymmetry were zero, no chemistry, if it were much larger, the universe might have collapsed too quickly or formed radically different structures. This razor-thin balance is not just convenient, it's foundational. Biology is physics. Your thoughts are electromagnetic interactions among atoms. Among atoms, atoms exist because protons survived annihilation. Protons survived because of a 1 in a billion imbalance. So when you wonder about purpose or meaning, you are literally the product of a microscopic symmetry breaking in the first fraction of a second after the Big Bang. Have you ever seen antimatter? Probably not. Because when antimatter touches ordinary matter, like the air around you, it vanishes. We can create tiny amounts in labs like CERN. There, physicists smash particles together at near light speed, briefly recreating conditions of the early universe. Antimatter appears and disappears. We trap it in magnetic fields suspended in vacuum because if it touches the container walls, gone. The fact that your coffee cup doesn't annihilate into gamma rays right now tells you something profound. The observable universe is overwhelmingly matter. The asymmetry won. But here's the philosophical pivot. This imbalance means the universe is not perfectly symmetric. It is not perfectly clean. It is slightly biased, slightly messy, and that messiness is everything. Perfection would have erased us. A flawless symmetry would mean no galaxies, no stars, no carbon. It's the flaw, the tiny crack in the equations, that allowed complexity to bloom. Think about ice melting. Entropy tells us that ordered structures tend to dissolve into disorder. Ice becomes water. Water evaporates. Stars burn out. Water evaporates. Stars burn out. Life itself is a temporary local rebellion against entropy. We maintain order by consuming energy. And yet our very existence depends on an earlier asymmetry, a break in cosmic perfection. So the story of matter versus antimatter is not just about particles. It's about why complexity exists at all, why something exists rather than nothing, why the universe didn't cancel itself into sterile equilibrium. And here's the humbling realization. The laws of physics don't care about you. They don't aim for life. They don't aim for consciousness. They follow mathematical rules. And yet, because those rules contain a tiny imperfection, you are here, not as the center of the universe, but as its consequence. You are what happens when symmetry breaks, when annihilation almost, but not quite, succeeds. Let me ask you something. If the universe had perfectly annihilated into light, would that have been less beautiful? A vast sea of radiation expanding forever, no observers, no suffering, no joy, just photons. Is beauty only meaningful because someone is here to witness it sit? Maybe existence is not inevitable. Maybe it's fragile. Maybe it hangs on one part in a billion. And that fragility is what makes it extraordinary, because the next time you look at your hand, remember those atoms survived a cosmic war. Matter versus antimatter, in near-perfect cancellation. And the reason you can wonder about it is because the universe was slightly unfair, slightly biased, slightly imperfect. And that imperfection is the crack through which reality emerged. So the universe should not exist. But it does. And you are the proof. The laws of physics say symmetry is elegant. Reality says symmetry broke. And in that breaking, stars ignited. And somewhere in one small corner of a galaxy, the universe, it began asking why it exists at all. That's you. So here's the final question. If everything you are depends on a tiny asymmetry in the first second of cosmic history, what does that say about how precious existence really is? Divergent. Let me know what you think. Because in a universe that almost wasn't, the fact that you can think about it might be the most miraculous imbalance of all.